Vedanta publication presents ICT-based teaching materials. Read, lead, and succeed.
When we learn how to calculate the measurements of three-dimensional curved surfaces, it often feels like an exercise in memorizing disconnected rules. Standard geometry curricula typically present the volume of a cylinder as πr²h and the volume of a sphere as 4/3 πr². We are taught to treat these as separate mathematical laws, existing in isolation from one another. In reality, these shapes exist on a unified geometric continuum, where the properties of one dictate the properties of the other. We can derive the exact surface area and volume of these solids from first principles, without the need for rote memorization. To demonstrate this, we will use two specific conceptual tools: the two-dimensional net and the Archimedean bounding ratio. By identifying this underlying logic, geometry ceases to be a memory test and becomes a precise tool for analyzing the structure of physical space. Archimedes of Syracuse was the first to identify the hidden geometric links between different three-dimensional solids. His proofs for these relationships were so mathematically rigorous that they were preserved in ancient manuscripts for centuries. His work confirms that our three-dimensional reality is governed by simple proportional rules. We define a right circular cylinder as a solid generated by the revolution of a rectangle around one of its sides. To find its curved surface area, we must find a way to calculate its three-dimensional surface using two-dimensional mathematics. We do this by unrolling the cylinder into a flat net. The width of this rectangle corresponds exactly to the original height of the cylinder, or h. The rectangle's length equals the base circle's circumference. Unfolding that boundary forms a line with the length 2πr. Since a rectangle's area is length times width, the cylinder's curved surface area is 2πrh. Its volume is found by taking the two-dimensional area of the base, πr², and multiplying it by the vertical space it occupies. By converting these curves into flat planes, we ground these formulas in basic, observable geometry. This logic applies directly to engineering, like calculating the material required for structural tubing or iron pipes. To calculate the properties of a hollow object, we defined an outer radius, big R, and an inner radius, little r. The volume of the physical material is found by subtracting the internal cylinder's volume from the external one, giving us height times the quantity big R² minus little r². But how does hollowing out a solid cylinder affect its total surface area? While volume decreases, the surface area increases. We must now account for the new internal curved surface area, 2π little rh, in addition to the external surface. This is a critical constraint for engineers. Reducing the mass of a part strictly increases the amount of surface area exposed to the environment. We shift now from the cylinder to the sphere, a shape defined by curved surfaces that don't easily unroll into two-dimensional nets. To analyze it, we use Archimedes' model, a sphere perfectly enclosed within a transparent right circular cylinder. In this model, the cylinder and sphere share the same radius, r, and the cylinder's height, h, is exactly equal to the sphere's diameter, or 2r. Establishing this constrained relationship allows us to define the sphere's properties using the geometric logic we've already established for the cylinder. Archimedes' first major discovery was that the total surface area of a sphere is exactly equal to the curved surface area of this bounding cylinder. We recall our cylinder formula, 2πrh. By substituting the cylinder's height with the sphere's diameter, 2r, the relationship becomes clear. 2πr times 2r results in 4πr², the formula for the surface area of a sphere. For volume, Archimedes proved that the sphere occupies exactly 2/3 of the bounding cylinder's total volume. If we take the cylinder's volume, πr²h, and substitute h for 2r, the bounding cylinder's volume is 2πr³. Multiplying that cylinder volume by 2/3 brings us to our final result, 4/3 πr³. The ratios found in these formulas are not arbitrary. They are the mathematical result of how a sphere fits within the cylinder that contains it. We can apply this unified logic to a composite shape like the hemisphere. When a sphere is cut in half, its curved surface area is also halved. reducing from 4πr² to 2πr². However, cutting the sphere exposes a new circular plane that was not part of its original exterior surface. To find the total surface area, we must add the area of this new great circle, πr², to the curved dome, resulting in 3πr². Slicing or manipulating a solid requires us to strictly account for the new two-dimensional boundaries created in the process. Three-dimensional space is not a collection of isolated shapes with random equations. By understanding how shapes unfold into nets or nest within one another, we can map the underlying logic of the physical world. Geometry is a system of constant proportions, principles first recorded by Archimedes, that remain the foundational blueprint for modern engineering.